be level sensors. That's our next lab. Then after that, I think we do temperature sensors. I don't know if I made any changes to that or not.
You know something funny? I got that call up on my computer, and I'm looking over here, and I see your hair. I moved it around. I didn't know it do that. Did you?
No, I didn't know we was.
I did that low sensor thing.
Really?
Really? I didn't do that.
Well, it's not. Yeah, you don't have access to the same one I've got. I don't know what's going on. So,
another one in there.
proximity sensors, speed sensors, load sensors, level sensors. So I need to change the arrangement of my PowerPoints.
Well, somebody's drawing that. Oh, this must be. Oh, that's the.
You're on.
That's
the video.
Yeah. What's going on? Sorry about
You're looking at the last time I taught this.
Yep.
Did y'all have, did I give out the labs on level sensor? Huh? Okay. Yeah. So I need to make sure these are on the glossary. So the distance is what? And the level is the or an understood reference, right? You know what I'm saying? The height at which one material stops and another material begins. And our other material is usually air, right? Ultrasonics. What does ultrasonic sensor do? Measure the time interval between the sending and receiving the echo. Transceiver. So what is a transceiver? Well, it's a device that contains both the transmitter and receiver. So this is called a transceiver. And then we have analog and digital. So digital ultrasonic sensor is going to trigger when something is at a certain height, right? You understand that? An analog sensor, we would actually measure the time interval between it reflects back and then it would give us an actual signal that represents the height. Everybody okay? Now we do that. So now an analog would probably have an update rate. So if you ever saw a movie or something where the policeman is using the speed detector, and it actually varies with the speed of the car, right? And then they could lock it in on the high speed and store it. Digital sensor would trip. So the one that we have over on the Amatron line is a digital sensor that we have the ability to set the span. And what's the span when we talk about sensor? Yeah, the range between the range. So what we can do on ours is we can set a maximum distance, and then we can set a minimum distance. So if the unit is inside the span, it says it's okay. If it's outside the span, it says it's bad, right? So that would be digital. That would be a reference to a digital sensor. Of course, we have to set it up for a reference. So what we do on that one is we have two blocks over there, that one of them is the maximum height, and we put that under the ultrasonic sensor, and it's got a big U on the top for the upper limit, and then the other one we have has a big L on top of it for the lower limit. And then what we do is we put each one of these over ultrasonic sensor, and then we indicate this is upper, this is lower. So what we did is we gave our sensor what? A range. And we gave it the range or the actual what's the span. Are we okay? So that would be a digital sensor. So even though the sensing head itself is analog, we've converted it to digital inside the sensor itself. Are we okay? Can be designed to sense distance, movement, level of solid electric speed, direction, limited by the surface shape and the density. So the problem with reflected sound is that we have what we call soundproof rooms. If you go into a soundproof room, it's got stuff that completely does what? Absorb sound waves. And then we got a place like this that's got these concrete walls. And not only does it has a tendency to kind of amplify for us, right? Give us, in fact, we can have a real hard surface and the sound waves will literally hit it and bounce off. And if you were really, really good, right, you understand, and you understood the speed of sound at your altitude, you could time between when you hollered and when the echo came back and what could you calculate? You could calculate distance, right? If you knew the speed of the wave was moving, because when it hits something, it's going to bounce back at the same speed, right? And you can measure time, and this is what we do with ultrasonic. This is what submarine does when they ping something. So they send out a pulse, right? You understand, of sound, and then they time how long it does what take to get back, and then everybody knows where they're at. So subs don't use that method anymore much. They still have the ability, but normally now they use acoustic sounds and stuff like that. Very neat. So ultrasonic distance sensors. This is pretty close to the one that we have over on the Amatro line. It's just a lot bigger. And most of y'all don't realize that when you go and get an ultrasonic sound. So a lot of women do this when they're pregnant. They did this to me a lot because of the injuries I had. And that way they can literally look inside and see what's going on without exposing you to X-ray, right? It's one when I got out of hospital, I didn't glow in the dark. With X-rays and stuff like that. We can also use photoelectrics. Now, a perfect example would be that definite reflector that we talked about, right? And I need to add that to my. Yeah, that's what the mouse uses. It uses a definite reflective, which is a form of diffuse. But this guy is looking for reflective light at a precise angle, right? You understand? So that means we can use these guys to sense what? Distance. We have some, I don't know if this is in here, we have some that do this, where they literally have multiple light sensors, and each sensor would represent a certain distance, right? You understand? So if it reflected off and hit this one, it would be one distance. If it hits that one, it would be another. So here we're actually using the light to definitely reflect it, but we have multiple lenses inside our receiver that actually can give an angle, and the angle can be translated into distance. So yeah, we can use time of flight, which would mean we could actually measure the time we send out a light pulse and how long it takes to come back, which would be a very, very short time, right? Time of flight photo detectors, this is exactly what we just talked about. So these work exactly the same way that ultrasonics use. We send out a pulse of light and then do what? Time it takes to reflect back off the object that it's hit. So this is basically a variation of a diffuse reflector. Now what happens is that the amount that we get back, we're not going to change the speed, but the amount that we get back would vary with the color of the object we're trying to measure the distance from, right? That makes sense? Yes or no? Huh? Then ultrasonic level detectors. This is what they use down at the gas farm down in Keller. The big tanks down there, you know that is gas, that is not oil, that's the tank. You don't want to put electrical sensors down inside that thing, even though you could. They use ultrasonic. So at the top of every one of those big old domes out there, those big old silos, they have an ultrasonic sensor that they measure the distance. Discrete level detectors, this is what we have. What's that?
I guess it was that. I don't have the same guy.
So this is what we got, guys. We got discrete level detectors. We have two. They'll go back and get them. It's obvious. They're white. They got little levers on them.
I don't remember exactly how to turn the message. It's Sherry Davis, you know her.
I know that. Dr. Davis.
I don't know how I ended up getting them on my phone instead of here. I get them both now.
So here's our level detector. We have two types. Both of them work on the principle of a magnetic reed switch. So these are going to be digital, right? You understand that?
Yep. Solid state.
These are not solid state. These are digital. Be digital, what does it mean? It gives us two states. It either gives us a true or a voltage or no voltage, right? So these work on the principle of reed switches. So what we have, you can't see it, but if you look real close, there's a magnet right here. And then the reed switch is mounted down here. These are the two wires that come out of the reed switch. And then when we get it close enough, the reed switch closes, and then we would have continuity across here, right? That makes sense? And we can make it different methods. So what you remember, these guys will mount in all different directions, right? You understand, because of the spacing. So this is not necessarily the top. They just can't put the identifier on all four sides. So what we can do is we can use it for a charging system, which would mean it's looking for this guy to move in this direction like this, right? You understand? Or we could use it. I'm sorry. This would be for a charging system. So a charging system means we're looking for the level to go up, right? And then we turn it around. This could be used for a discharge system. Now, this could be used for charging either way. It depends on what you look at, whether the contact is open or closed. This works on a reed switch also. So this has a magnet in this thing. And when it moves up and down, it makes the reed switch, right? And we can mount this different ways too. This guy here is electromechanical. It's not electronic, it's electromechanical. Are we okay?
So that's based on a signal going to the.
No, what you mean?
Okay. I'm thinking, how did it work?
This is
power.
Well, this guy does not have to be powered. So what we would do is we would come over here, and then our float switch would be out here. That's what it is right there.
Okay, wait a minute. You can put this in some sort of fluid or something.
Yeah, the float switch would be in the fluid, right?
But I was thinking about that particular one right there. That don't go in fluid.
It does. It can. We're not gonna
do it, but it can. Okay.
Yeah.
Right.
Yeah. This is totally sealed up. So that's why we're using reed switches. Is that we don't have to make contact between the magnet and the resistant switch itself. But both units are completely sealed and submersible. Okay. So yeah, and it would be this guy right here. So this is the symbol, by the way, of a float switch.
So when the float goes up, then
Well, it depends on what type we have. Yeah, whether it's normally open or normally closed. So if we flip it over one way, if we flip it over, we'll have a normally closed, right? You understand? If we flip it over the other way, we'll have a normally open. You understand what I'm saying? Very simple device. It's used all over the place. Next thing we have is we have photo electric sensors. So what we're doing is we're using the through the beam, right? And we shoot it through the liquid or whatever we're trying to measure. And then when it comes up here and covers that up, it breaks the beam. And now we know it's at a certain level. We don't know if it's high. We don't know if it's low. But we could use them in combinations and set a span, right? You understand? So what we could do is we could have another set up here, or maybe have a set down here, right? And then we set the span. So this one would trigger when we hit our lower limit. This would trigger when we hit our upper limit, right? You understand? And this is a lot, yeah. This is a resistive probe. So what we're doing is we'll use a liquid that has, it's resistive, but it has conductive characteristics, right? You understand? And then what would happen is it comes up here and starts covering this up. Then what we're doing is we're changing the amount of resistance depending on the height. So this would give us a resistance that would be proportional to amplitude. We could use a float, right? You understand? So this is the float. This was on the big old water tower up above behind Bessemer, behind UAB West, is that they got a sight gauge on the side. And this is exactly what they're doing. So they got a float right on the rope, and it comes up, and then the dial on the side comes up and tells them what amplitude, what level. We can also, we've already talked about this, we can measure what? Pressure. We can measure weight and translate that into height. So here they got load cells on the bottom. This is what we use inside airplanes. The airplanes I worked on, it used capacitive sensors. And what they were a tube. So the two plates were actually inside a tube like this. And then it was opened up on the bottom. And then when the fuel came up here and changed that, it changed the dielectric, right? You understand? Which changed the size of the capacitor, or changed the capacitance, which gave us a reading of how much fuel was in. And these were capacitance probes. And what's nice about these is there's no current flow through them. So what you can do is you can put extremely high R value in series with it. So if something happens and they short out, it's not going to create any heat or anything to cause the fuel to catch on fire. So the airplanes that we worked on had used capacitive sensors. And it had them on the top and the bottom of the wing. And we had what we call, well, the planes I worked on, the P3 Orion, had a big center tank, which I forgot, it was like 5,000 gallons. And then it had wet wings, so it had two gas systems in there. The planes I worked on, we could stay in the air for 14 hours without refueling. So they had carried a lot of gas. What they had to do on the wings though is they put the sensors on the top and the bottom of the wing, and then they summed them together. So if the airplane did this, right, these guys would be covered up. These guys over here would be open. But when they did a sum of all the sensors on the wing, they got an accurate value no matter what through a Wheatstone bridge inside the indicator. But they summed all the probes together, right? You understand that? So what would happen if we was in a tilt? These on the outside of the wings would be covered up. These guys on the inside would be completely covered. The ones in the center and they would sum them all together, so they would get an accurate fuel reading, whether the plane was doing this or this or this, and we didn't fly upside down. But, it was a P3 Orion, which they're finally phasing out. They're going to a PA, which P stands for patrol.
That thing around.
So this is the planes I worked on in the Navy. Had 4 big turboprop engines. So turboprop engines are jet engines, but instead of using the force, they transfer it up to the top. So these were sub chasers. They're fine. They were ASW, or anti-submarine warfare. These guys could find and kill submarines. Underwater. They did it by this guy back here. This was called magnetic anomaly detector. And what this guy did, we called it the Stinger, of course. This guy right here sensed the flux of the earth. So what happens anytime you had something underwater that had a lot of metal in it, the flux of the earth would dip down into it. So they could tell when they was on top of it. They used sonobuoys that they launched out the bottom to find it. And they would do it in a U-type shape. And then they had sensor stations that they would pick up the sound coming from the props of the submarine. And then they could see about where they was at. And then they would start flying with the mad gear, and when they had a dip, they knew they was right on top of it. And then they stayed on top of it. So we would swap out. In fact, this. Did the submarine know? If they was listening, they would. They could tell if they listened. The submarines have acoustic detectors too. That's looking at the surface and they can pick up props and everything of ships moving through. So they could tell. We carried signatures. Once we identified a submarine or even a boat, it was the neatest thing. Every prop or screw or wheel, whatever you want to call it, the prop, every one of them generates a unique acoustic signature. And believe it or not, they kept records. Every time they found one, they would keep a record for it. And then after that, if they ever picked up that acoustic signal, they'd know who it was and what type of ship it was and how deep it was. And the only thing they could do is go below the acoustic layer. You know, there's an acoustic layer in the ocean where you have the warm water and cold water on top, and it basically blocks anything. So if the submarine stays below the acoustic layer, you can't find them. But they have to come up sooner or later, right? So as soon as they we could find them. In fact, we found some of them on the surface too. That was a big deal. So that's the mad gear back here. And then these slots, this is where we shot the sonobuoys out on the bottom. We get down about 100 foot off the water and shoot those sonobuoys out. And they'd feather the 2 output engines. Feather means they take them and turn them into the wind so they don't spin. And then they'd fly on 2 engines. The plane could fly on 1 engine, but it ran forward. Had 460 kVA generators out there on the. So these are P3s. So this is where I started into electronics, guys. So before I got in the Navy, I was a stock clerk for a grocery store. And then I is an aviation electrician's name, which is kind of misleading because we dealt a lot with electronics in the Navy. So in the Air Force, all those people do is work on planes. In the Navy, you're sharing your troops between airplanes, you're sharing them with ships and all kinds of stuff. So every trade, every MOS has a cross trade. So we had true electronics people, but they worked on the radars, the sensor stations, and then the communication systems. And then they had AEs, were the electricians. We worked on all power and distribution systems. We worked on inertial navigation systems, also the autopilot. So it was a cross between us and electronics, and then the ATs, which were aviation. I forgot what AT stands for. We wouldn't. Yeah, so we worked on a lot of electronics, and plus Well, I didn't actually work on the electronics because I was what they call O-level maintenance. So we did swapping. So if the flight computer went out, we'd swap it out, but we'd have to determine if the flight computer was bad. And then we'd send that back to AMD and they would fix it. That makes sense? Oh yeah, I've been all over the place. Huh? I've been all over the place. Well, not true. I was in the St. Pat fleet.
The military is a very good training. You get trained very good.
Yeah, and very young too. They give you a bunch of responsibility early.
I know they give you confidence too.
Yeah. So I was a shift supervisor. I was 20-some years old. I turned 21 when I was in there. And I was a night shift supervisor. I was a CDI. CDI was people that inspects other people's work.
You know, I never was in a situation where I didn't feel like I was trained enough. You know, that's right.
Yeah, they train. They have to, and they give you a lot of responsibility. So this guy here had it was called wet wings. So the wings carried fuel, and then also it had a center tank that carried fuel. I forgot how much, almost 10,000 gallons of fuel this thing could carry. You know. And the P3, last time I checked, still holds the speed record and the altitude record for a 4-engine turboprop plane. So we could cruise at like 35,000 feet, which is up in the commercial. In fact, that's what we used to call it. Flying airways is what we called it. And then we could get down right on the surface of the water. I mean, about 100 feet off the water while we was looking for submarines. It was strange. You'd fly by a ship and you were below the superstructure of the ship. A plane this size. I carried a crew of 13, and then we huh? No, it wasn't cargo. We carried stuff that people bought. So we'd go to these places like Thailand and everything, and they'd make runs out to the Philippines to get San Miguel beer. I don't know if that's her. And they would put it in the Bombay. So it had a full-blown Bombay door here, and then it had hard racks over here. We could put missiles and everything out here. But it carried, and it was nuclear capable, which means we could carry nuclear bombs. But what they do, they had a special rack that they would actually snap up into the mounts of the Bombay, and they'd fill it full of beer. So they'd make a beer run. They'd fly these $32 million plane down to the Philippines and bring back a bunch of San Miguel beer for us. But we also put luggage and stuff in there. And then they had a wire, they had a mesh that they could put down one side of the tube and put stuff in there. So we'd go off to, you know, Iran and places like that. So I've been to Iran. We'd go there now, but, we were there when the Shah was still in power before that. Huh? Before things got real, yeah.
I worked in the air back. We had a guy who come back with these little Honda mini tops.
We had guys buy motorcycles. They didn't ride them because they didn't have licenses in Japan, but they bought motorcycles. We bought bicycles. Stereo. The big thing I bought was stereo and photographic camera.
But he was buying them little mopeds. And you couldn't bring a new one in just to bring a used one in. He'd ride it around, get it dirty. It was used.
Well, they had ship out, so they'd bring a big cargo plane in and we would load out and they'd put these big containers when we get ready to come home. So we bought tons. Ultrasonics, everybody okay there? Capacity, load cell, pressure, and then that's probably it on that I know of. And then of course photoelectric, which is not in this section.
So ultrasonic probably will. I'm thinking about call. I don't know which one of the calls.
This is the most popular used right here. It's just a basic float. We go up there and make it float. It rises when it comes up, goes down. We'll put a Hall effect. I've seen Hall effects inside here too. And then the float will have a magnet in it, and it comes up through the Hall effect, and the Hall effect gives us a reading, right? You understand? I've seen potentiometers used where they just come up here and this thing moves and it actually moves the potentiometer, and that way we get a voltage that's proportional to the weight. But the pedometer is just a basic float. Very, very simple. And it's been around for years. This is what's used in your car. So if you ever pull the actual fuel cell sensor out of your fuel cell, it's just going to be a basic float connected to a potentiometer. And then that comes in. Then they have an A to D converter inside your body control module that trips now that says once you exceed a certain, go down below a certain voltage level, it means you need to stop and add fuel. So odds are, you think about the number of vehicles out there that's using that technique just to float.
Don't have to be fluid either. We had chip dams. When the chips got up, it's the same thing.
Just push something out of its way. Yeah. So this is probably the most popular. Even in small aircraft. In big aircraft, though, they use capacitive, but it still don't make any difference. You compare the number of automobiles compared to the number of airplanes. The float is far by far, but what they do on that is they don't use a limit switch. They use a potentiometer, right? In fact, that's the one I gave you on the test. That's basically that's basically a card. That's a card. That's it there. And then they bring it into your body control module, and it goes to an A to D converter, and then it displays it on your fuel gauge. And I don't even know if they take it to an A to D converter anymore. They could, right? Because most of our fuel gauges are still what? They're still analog. So I'd have to see if that even goes to the control module. If they actually take the output of if they take the output and take it directly to your fuel gauge, but it's got to go into your body control module to turn on that low fuel light. That's by far the most, not float switch, float with something. So the float is actually the sense head, right? And then we combine it with something else to convert it into a sensor. And we'll see a lot of our sensors do that. We take two units, we have a sense head, and then that sense head converts it into what? Into either a voltage or a current. Are you okay? So here they're using a limit switch, but your car uses a potentiometer. Are we okay? That's level, guys. There's not much to it. So what do we got? Got ultrasonic. Everybody okay? Got any questions there? We got photoelectric. Anybody anything there? We have what we call the definite reflective, and then we have time of flight. Y'all understand those, right? Are you okay? And then there's ultrasonic again. I need to move that. And then we have the discrete level conductors, right? So these are discrete, which means these are going to give us digital out. I don't know about this guy. These two are definitely going to give us digital out. And then we have the analog, but they don't show this. So I need to come back and look for something, because I know for a fact that we can take this and hook it up to a potentiometer and get a voltage that's related. That wouldn't be discrete. Are we okay? Any questions? Okay, guys, y'all can go lab. I'll put the test review up there.
You understand it?
What do you mean? Oh. Okay, I don't know what you mean. Pretty.
So they're saying when a car is not pretty,
yeah.
So you should be able to push the button.
No, only thing to push the test button is going to be on the right or left line, right?
Yeah, but they're saying the car's not good. The car's not good.
occasionally the test, so this is just saying why we would need that. The occasional test, we occasionally test the red lamp to make sure it's working. That's it. And so what would happen if the red light wasn't working, it would, if the red light didn't work, then we could have this problem right here, right? You understand? Or it could go past the limit. So that's all this is saying, is that we got a push button that we can test to make sure the red light's working, because that's when, that tells the driver to do what? Stop. Does that make sense now?
Yeah. It's required that it can be checked for red light when no vehicle is present.
So that's all you do, and you just come up here and press it, and the red light comes on. No matter if there's a vehicle there or not a vehicle.
Well, it's not. Well, we can't get it to work. It only works when the timer times out.
Well, then you need to bypass the timer. So it's a very simple correction, right? Understand what I'm saying? So you take all this control up here, I don't care what it is, but if you put that push button over here, right, bypass all the decision making, then if you push that, no matter if it's off, it's going to do what? It's going to come on. So all you got to do is just put that push button, just jump out all your other timing. Your normally closed, I think you got your timer contact, and you got another contact in there. Just jump those two things out. That makes sense.
Oh, well, that's it. I think these would be okay to use. I'm not gonna.
As long as they got rubber, yeah, these would be fine. For what the voltage levels that we're dealing with, those would be fine.
Well, they were like $5 a dozen. I thought I might just leave some here.
And they're pretty too. And they're pretty too.
They'd be cheap. You know, in case somebody forgets something.
Yeah, they're doing motor controls here, so you know you could leave them in the drawer, but I can't guarantee that they're going to stay there.
I think my partner's got something.
Somebody turn on the lights. So we can see the lights, you know.